Thanks to Matt and Mux and Heavybit for hosting. Holographic video is kind of a provocative title, and I guess we're going to delve into what exactly that means. Mostly, it's going to mean VR and some other stuff. So a little quick caveat. My company, Visby, is working on a type of VR and AR technology, light field compression and so on. So that's my perspective on this. It's a narrow perspective on the industry, so take it with a bit of a grain of salt if you can. Holographic video. The reason that I think holographic video is worth talking about, frankly, is we have these new categories of displays that are, I like to call them functionally holographic, right? You put on a VR headset, you put on eventually these AR headsets, and as you walk around a space, you expect to see new perspectives as you move around. You don't want to see the same pixels just kind of moving all around. And that's basically a hologram, right? You're moving around and seeing different perspectives. However, that's really just the tip of the spear, right? There's actually a whole bunch of new multi-perspective displays coming out as well, panel-based displays, planoptics displays, and so on. And what we've found is that the hardware out there is actually run way ahead of the software stack. The displays are capable of this multi-perspective imaging, but the software stack is kind of almost all the way there, and the video stack is nowhere close. So, what does that mean? Okay. We talk about the software stack not being there entirely. Jump right into the standards bodies. I'm sure everyone around here probably gets their hands dirty a bit with the various video standards and so on. They're not really giving recommendations yet. I've been to a couple of conferences, and it's kind of a big, glorious mess. I'm not going to delve into all the bullet points here. I'm just going to show you the SMPTE committee workflow for how to arrive at a standard, and understand that it's just not really anywhere close. If you want to learn more about that stuff, it's fascinating to follow. It's worth following. These are the two sources I think the most worthwhile. There's a great report from JPEG Pleno that covers pretty much the entire breadth of possible holographic approaches. And then there's the SM Fold conference that I attended last year. All the sessions are up on YouTube. Definitely worth a look. It's like I said, it's a good survey. Okay, so this is sort of the landscape, right? We've got some standards bodies that are trying to figure things out. We've got sort of a lot of people trying to think about the software stack, but there isn't really a solution you can go out and buy there. So what's actually going on in the industry? What are people doing in VR? What are people thinking about in AR? A whole lot of different stuff. But to understand it properly, let's back up and talk a little theory, okay? These devices are 6DoF devices. Everyone here familiar with VR and AR? Raise hands. Who's had a VR headset on? That's not a Google Cardboard device? Okay, good. So functionally, the critical thing to know about these devices, what makes them holographic, is when you move around, you get new perspectives, right? So you put a Google Cardboard on and you can look in any direction and see new pixels, and it's lovely and wonderful. But if you take a step forward or a step back, you got the same pixels to look at, right? So that's a 3DoF device. The devices I'm interested in are 6 degree of freedom, okay? Which is to say you can translate in 3 dimensions and you can look in 3 directions. The history of these headsets is kind of funny. There's sort of these 0DoF devices out there, which are no really different than sticking a TV on your face. No matter where you look, you're seeing the same pixels. There's the 3DoF devices, like a Google Cardboard class device. Again, you can kind of look in any direction, but you have no freedom to move around or walk around. What you basically have is this little window of pixels that are kind of cropped in from a larger set of pixels. But it's always the same set of pixels. And that's convenient. It can kind of piggyback on today's video standards, right? But it's not really fully holographic, okay? But that is the state of play today. You're basically just pushing and mashing around these pixels. That's 360 video, stereo or otherwise. That's Google Cardboard. I don't think that's the way of the future, though. The way of the future very much are these 6DoF devices. Today, that means the Oculus, the HTC Vive, the PSVR, and then lots of other kind of smaller players in the space. The critical thing is, as a dev, when you're trying to deliver content on these devices, you have access to those 6 degrees of freedom. The XYZ position of the viewer, and then the exact direction they're looking. The other thing to know, of course, the display has to be 6DoF, but then the content has to be also. And that's, I think, the real gap in the industry right now, and kind of what motivates a lot of the thinking around holographic video codecs. So right now, 360 video is really the state of play. In practice, it's got to be 6DoF down the road. And the reason for that is the mobile VR market is moving to 6DoF. I think we're just probably a year or two away from that. So by the time VR kind of matters as an industry, the current 3DoF approaches like 360 video might start to be a little bit deprecated. Okay, so that's kind of the backdrop. If we're worried about where this is going to go in the next couple of years, you got to be 6DoF, you got to have something functionally holographic. There are really fundamentally only 2 good approaches to holographic content right now. A general class of volumetric video, which is closer to market, and there's actually some companies working on that, and then this kind of more theoretical light field approach. That's what my company's working on. The polygon model, or the volumetric approach, is one that basically just treats the world like a video game. Whatever content you want to display, you represent as a series of polygon meshes that you then wrap with textures. There are some advantages to that, and there's some disadvantages. The light field model is totally different, and I want to just pause for a moment and distinguish light fields for 6DoF headsets, light fields for holography, from light fields for refocusing, okay? There's a lot of muddling of terms there. Refocusing is interesting. It's totally outside the scope of what I'm talking about. When I talk about light fields, I'm really meaning all of the light rays that you could see in a scene. I'll explain that a bit in a minute. First, though, life is a video game. If you're trying to represent holographic content in a headset today, the standard thing you do is you basically make a video game, right? You encode polygons, whether they're computer generated or somehow derived from the real world. You have some sort of texture, 2D texture you drape over your polygons. And then as the user moves around, you can use this game engine stack to play the whole thing back. It's effective, it works, and it looks like a video game. That's good and bad, right? So you're sitting on top of this entire very mature technology stack, but it will always look like a video game for that reason. Also, it's not really video, so I presume no one here really cares about that. One of the main problems with volumetric, by the way, frankly, if you're concerned about the real world, is capturing the world as polygons is not really a mature technology yet. There's a handful of techniques, but it's all defined by this need to generate your polygon maps and then have your texture maps. Now, the texture maps are pretty straightforward, right? Traditional cameras, you kind of know what color things are supposed to be, but getting the polygons is a little tricky, right? So there's a combination of different ways of scanning the world. There's some people who use LiDAR, some people use like a structured light type Kinect-like approach where you cast a pattern over the scene with IR and then try to look at how it gets distorted. Or you just use lots and lots of cameras and some big computer vision techniques and try to infer the structure of the scene from multi-perspectives. There are problems with all of this, but that's sort of the state of play right now. And then at the end of the day, once you're playing this device back, you're running a game engine. So think about how much compute power gets thrown at a typical like AAA title video game these days. And if you want your volumetric video to look good on, say, mobile VR on someone's phone in 2 years, just think about the mismatch there between the GPU on that phone and the computation required to render a super high polygon mesh and textures and everything else. And see there's a conflict there. Now, I mean, Moore's law, everything's going to get better and easier, but that's sort of a tension with the polygonal approach right now. There's also problems with the capture side, frankly. I mentioned these different approaches to getting your polygon model of the world. They kind of break down in a lot of ways. There's a trade-off between the density of your polygon meshes and how accurate it is, how consistent they are over time. Do you enforce things that be rigid and then everyone's clothes looks all funny? Or do you let them vary over time and things that should be rigid aren't, kind of like a wavy edge to them? That's literally where it is today. If you go look at the sort of like leading polygon-based volumetric producers, you can kind of see those trade-offs and how they made their choices there. Unfortunately, it's kind of grounded in that technology today, right? There's no way to get around the fact that you've got to have polygons somehow and you got to get your textures. There are a few things people are doing to make them a little better. A key one is if you can kind of reduce your polygon meshes in an intelligent way, that totally reduces the compute time on the client side. It's maybe a less bad trade-off against fidelity if you're intelligent about how you decimate your meshes. And then you can actually get away with a fair amount of detail in your textures, not in the polygon models themselves. I kind of like this Trump Loyal painting from the Samsung, I think it was the S6 launch, not the one that would blow up in fire and stuff. They painted this woman to appear like she's got this like charging cable on her neck. And it's effective from a particular angle, right? You can sort of look at it, it looks like there's some shape there that doesn't really exist. So it's sort of like trading off some of your polygon shape into your textures, right? So these are the kind of hacks people are using in the industry right now. At the end of the day, though, to be completely honest, this is just like a really powerful VFX shot, right? If you're used to setting up a camera and shooting and compressing and delivering and everything being clean end to end, that's not like that at all. In fact, the truth is the entire VR industry is all about like very broken workflows and like funky one-offs and things being kind of weird. And in practice, a lot of these approaches have already been used in the film industry. So they're porting over VFX techniques into VR production and sitting on top of a video game stack, which is kind of an interesting fit. That's also why it's close to market, right? The polygon approach is using a couple of fairly mature technologies and colliding them in a new way. In contrast to that are light fields, this sort of like kind of very, very new way of representing light to the world, right? Now, if I can back up a step, the reason I'm interested in light fields, frankly, is I'm not big into VFX. I'm not big into video games. I want to see the real world represented correctly. I want to see it represented photographically. And that's what motivates the light field approach. Fundamentally, the 3D polygon approach says, let's take the world, let's try to represent it as polygons, and then use that to calculate and infer what light you would have seen if you were in the scene itself, right? Because these devices, the headsets and so on, are devices for pouring light into your eyes, right? At the end of the day. So you go from light to this polygon model, back to light again. And this sounds a little silly, but like, why don't we just deal with the light in the first place? And I've got a few slides to explain why that's not a good idea, but that's what we're doing. We're working on sort of a purely photographic, purely light field-based approach. The truth is, the main reason is that when things are photographically correct, they just look better. Some things don't fit into a polygon-based representation, right? Some things don't have a well-defined shape. Some things don't have a single texture or color, no matter what angle you see them from. Some obvious ones are reflective surfaces. As you move around, the color on a particular region will change, obviously, as the specularity of the light changes. Fog has no well-defined shape, or smoke. Things that change quickly over time and have lots of spatial structure to them, like water, do not look good in polygon-based approaches. And all of these things actually come and collide when we talk about the human face. This is like the one piece of subject matter we care about the most, right? Any content we care about has people's faces in it, and our brains are highly tuned to understand when human faces don't look quite right. And it works in very strange ways. The little glimmer in your eyes, a little bit of sheen on people's skin. These are what allow us to tell in an instant the difference between a live human and a wax model or a dead body or what have you. And so for us, that's kind of like the really strong lever for why a more photographic approach is highly motivated. Now, what are light fields? How do they work? I think I mentioned this earlier. They're not for refocusing. That's a super interesting technology. It's basically irrelevant to what we're talking about today. There's some crossover, but there's basically a massive scale difference. When we talk about using a light field for refocusing, we're talking about how light moves and changes across the aperture of a camera lens, typically millimeters in scale. When we talk about light fields for VR, we're actually talking about something much, much larger. And here's why. If you see something, you are not actually directly apprehending its 3D shape. What you're really doing, of course, is you're inferring its 3D shape, mentally, but you're taking a series of point samples of the light field as it bounces off of an object, okay? So all the light bounces off the thing you're seeing and comes into your eyes. So now, if you imagine that light and you would actually sort of capture it and recreate it exactly as it was, you would effectively have a hologram, right? You'd see every possible perspective. As you move around, you'd see the correct reflectance. It wouldn't matter what the underlying shape was. You'd be able to figure it out. So fundamentally, if you have the light rays, you don't need the model. This is the more direct approach, right? And this is why it works for VR and AR, right? It's if you've got a whole bunch of these light fields, which have all the ray data, all the light rays you could have possibly seen, then as long as the playback device can figure out what light rays you would have seen, as you move around, they can kind of pick among them or render them or recover them and deliver them to your eyes. And it'll be like you were there in the first place, right? Goat or no goat, polygons or no polygons, you're going to see what you would have seen. Kind of no apologies. The downside is it's just a colossal amount of data. That's fundamentally the biggest problem. There's other problems as well, which we'll get into, but that should be in the back of your mind at all times. The light field approach is a big data problem. And part of the reason is, if you look at a traditional light field camera, they look kind of like this. This is from the early 2000s, Stanford kind of light field camera. And it's kind of a very straightforward approach, right? If you want to capture all the light across a large area, you just cram as many cameras together as you can. This is a company called Otoy down in Los Angeles. They do primarily 3D animation stuff, but they also have very strong in light fields. They put together this little gantry and spun a DSLR around for 3 or 4 hours and produced one frame of light field, right? And the idea was they had, I don't know how many 100 photos every millimeter or so, and then they knew what light rays were impinging on that space. And I think they were very careful to have absolutely no one walking through their office while they did it. And then you could sort of figure out what light rays were there and sort of infer a light field from that. There's also, obviously, the new Lightro Emerge. Again, same idea though, right? You're looking for as many light rays as you can, so you pack those cameras as tightly together as you can. And this is sort of what creates this big data problem, right? If you have to have all that light, you gotta really have as many cameras as possible, as close together as possible, which just means a lot of data. There's actually a bigger problem though, beyond the data, and it's optics and aliasing. So if that's your light field camera, right, a whole bunch of cameras packed together as tightly as possible, it's actually not a great way to measure a light field, just because you're using traditional 2D lenses, right? And I've sort of highlighted here just a traditional wide-angle lens. The red area, kind of hard to tell, is the aperture, sort of the iris, and the green dot in the center is the clear aperture. So the only light that passes through the lens and actually creates an image passes through that millimeter or two gap in the middle, and the rest of the light gets rejected. So even in the best, fastest lens light field arrays, you're throwing away well over 99% of your light. It's not generally a problem to throw away that much data. The problem is that if you're throwing it away and you're not low passing your signal, anyone who's in audio here knows, you're going to have like some very serious problems. And in a light field, when you start to alias, very strange things happen. So I've got this picture of the light reflecting off of the water on the bow of a boat. What that represents is if your eye was where the boat is and you moved around a little bit, you would see the glimmers and so on the water changing very quickly, right? That's what that reflection is. It's basically an image of the sun on the bow. What that does in an image is something like this. Here's an example of aliasing in a 2D image, right? If you low pass, you just throw some pixels out and don't bother to average them, you get these strange Moire patterns where high frequency signals end up being represented as a lower frequency signal. Now what that looks like in VR is a little odd. We'll talk about it later. But needless to say, it's a pretty horrible artifact, and it's a major problem. So in addition to the big data, you have this aliasing problem. You also have an interpolation problem. I mean, fundamentally, if you've got this array of cameras, you have a pretty good idea of what someone would see if their eye was right there where the camera was. But as soon as they take just a little step to the left or right, you have absolutely no idea, right? You have to interpolate what they would have seen, because you've thrown that light out, and you've got to recreate it properly, right? So you can think of interpolation as sort of being the dual of the aliasing problem. And any approach to light field is going to have to solve that. The data obviously is a massive problem. The good news on the data is that it's generally pretty redundant. If you think about a scene, almost any normal scene, if you move around, the scene doesn't change that much as you translate, right? There's a lot of entropy in the sort of angular space, but there's not all that much in the spatial space. Now, how you choose to leverage that redundancy is kind of what's going to make or break the approach. So the truth is, the way that most companies that are starting to look at light fields right now tackle these problems is actually by muddling the two together. One of the best ways to know how your signals alias or don't is actually to apply a polygon model to it. So, two of the big names, Lytro and Otoy, that are working in light fields right now, both are using polygons and light fields, it's a strange deal with the devil, to be honest, right? You have sort of some of the advantages of both, but you kind of also carry around some of the problems of both, okay? So you solve your aliasing problem in that if you know the 3D structure of the scene, you can sort of figure out where the signal really is in reality. And you don't get these low frequency aliasing problems. You basically use your 3D model as a clipping mask. That's my understanding of what Lytro might be doing, just looking at some of their output. On the other hand, at the other end of the scale, you have Otoy, who's much more a polygon-based company. They look more about 3D structure of scenes, and they're interested in light fields. And what they have done is they've sort of taken this BRDF approach, in which you sort of say, okay, well, the scene substantially is composed of 3D objects. 3D objects have a structure and they have some color, generally. And if you look at some object point, it's mostly the same color and brightness, no matter what angle you see it from. But there's this gloss of specularity that sits on top. So my understanding of what Otoy has done, just kind of reading some of their publications and hearing their CEO speak, is they start to look at this bidirectional reflectance distribution function, and they separate out the specularity, and they layer this gloss of light field on top of a high-resolution polygon model. Totally valid approach. It's also pretty data intensive, right? You kind of are carrying around these polygons and these medium-resolution light field kind of texture maps. And the stuff looks beautiful, but it's sort of it's punted on the data problem in return for getting your aliasing problem handled. Now, this is where we kind of go to the next step, and this is kind of a big one, is what happens if you have a pure light field? If you don't have polygons, how in the world do you handle a sort of pure light field approach? And this is kind of where we kind of like to turn off the recording devices, kind of go a little off the record. This is what my company is working on. Visby, we're doing fundamentally a pure light field approach. And I think it unpacks some really interesting problems with the space and sort of possibly shows a way forward.